Hello, everybody. My name is Kevin. I am here to present to you our project on stock analysis. So, to preface, the United States stock market stands as the world's most dominant financial market, accounting for nearly half of the global equity capitalization. Within it, seven major technology companies: Apple, Microsoft, Amazon, Alphabet, Meta, Tesla, and Nvidia, correct, collectively known as the Magnificent Seven, also Magnet 7 for short, have become the main drivers of market growth. In fact, the combined market value is estimated to be around 60% of the US GDP. However, despite their surge in retail interest towards these companies, most trading tools available today, such as TradingView and MetaTrader, often pose barriers to newer traders due to high subscription costs and complex interfaces. Our project aims to bridge that gap by creating an accessible and reliable Python-based web application using Streamlit. The application retrieves real-time and historical stock data from Kaggle and visualizes it through interactive charts. It also integrates several key technical indicators, including simple moving averages, upward and downward run indicators, and support and resistance lines to help users identify trends and potential entry or exit points for trades. Most of our algorithms achieve linear time complexity, which means that it's very scalable for larger data sets. So if you want to use data sets for more than just the Max 7, you can choose to do so. Our algorithms are very good. In essence, our Max 7 stock analyzer empowers traders, regardless of experience level, to perform their own technical analysis efficiently, providing a simple yet powerful tool to enhance decision making and maximize profit potential. So now let's look at the file structure of our project. So there are three main directories: the data, graphs, and utils directories. The data directory handles everything data related. Graphs handles everything graphical related, and utils is a miscellaneous folder with all the miscellaneous functions. Basically, any function that doesn't belong into either the graphs or the data folders, they get put into the utils. Mostly, the functions in utils are the functions that are used by every other function in the project, such as wrappers. These wrappers actually help to actually measure the amount of time taken for a function to run, as well as the amount of memory being used by the function, as well as the data set, the data structures, the ruling mean, and the upward downwards array. But I'll be explaining all this in more detail later on and next profits. And yeah, okay. All right. Okay. I think it would be best to explain the data structures right now because a lot of the functions in data wrangling are actually using the data structures. So I'll just start the explanation first. All right. So this class, the rolling mean array, is actually a custom implementation for computing rolling averages. It's similar to what Pandas does, but without external libraries because this module focuses on programming fundamental skills, which is why I decided to do it. And Pandas will always be a lot more efficient and a lot faster than any of what I can program because Pandas is programmed in C. I can never hope to manage uh, the performance of Pandas, but I can hope to try. As you can tell later on, I did try to measure up to like pandas methods, and I would say that I got pretty close, but I'll show you later. Okay, okay, so it's designed for efficiency and low memory usage because of these slots, yeah, this slots uh, attribute. It checks for this. It takes these parameters, the datas and the windows. And of course, it takes the data length, but that's not a parameter, that's just here. Yeah. And also it takes these predict steps for this predict later on. So this function, it calculates the moving average efficiently. So instead of actually calculating the sums for every window, it uses a sliding window technique, subtracting the oldest value and then adding the newest. It reduces the time complexity from O(n) times W to O(n), basically a linear function. So the dot predict, it's a static method because it's actually not being used in a lot of my fun a lot of basically this class is being used in a data wrangling, but this dot predict is not used in the data wrangling. It's actually used in the dot in this graph that I find out. But I do not want to just have to either first of all export this entire array as a pickle file, and I also do not want to have to store this dot predict in some in that data frame somewhere so that it can be exported out. I don't believe so. Either that, or I also don't want to have to recall this whole entire class. That's just incredibly inefficient, which is why I decided to make this a static method. Because logically, it makes sense for this dot predict to be inside this inside this rolling mean array, because it's a method that uses the rolling mean. But I decided to just use it as the method itself. So what's the difference between naive rolling mean and rolling mean is that this one, it does not use a sliding window approach. The reason why I have this is simply just to showcase the performance difference between the naive rolling mean and the rolling mean inside the data wrangling. I will show it to you later. Okay, so the upwards downwards array, it's designed to analyze trends in numeric data. Specifically, it identifies whether the data is moving upwards or downwards over time. So it just takes the data, and also it uses these slots in order to reduce the memory requirements and also to reduce the time taken for accessing these attributes. And yeah, so create run group. It's basically the optimized version that computes the difference between the consecutive values in place. If the difference is positive, it is marked as a one. If it is negative, then it's going to be negative one. And if there's no changes, then it's just going to be zero. And the naive run group is just a simpler and slower version that recalculates the differences without modifying the data directly. It's just for comparison's sake. Okay, now we get on to the wrappers. So this is actually a very useful wrapper. It's just before the function runs, right? It starts tracking both the time and the memory usage using Python's time and however you pronounce this modules. It then executes the target functions with all of its outputs, and then afterwards it records how long it took for it to happen, and then it measured and also the peak memory consumed, and afterwards it prints it out. And basically, you'll notice that a lot of my functions, I actually wrap it using that wrapper in order to just measure the space-time complexity as best as I can. All right, now we get on to the data wrangling part. So before I get onto it, you need to understand that when it's installed from Kaggle, the data, you need to know that it's in this format. Basically, each company has their own data sets, and it's actually very inconvenient. So what I did was that I basically have this function. It's called select target CSVs. And I compare it using the non-recursive method, which is basically the only difference between these two is that one uses scan directory and one uses list directory. So the scan directory is efficient because it gives access to the file directly while scanning. It checks each file in the folder, and if the file name matches one of our target stock because it adds it to the results list. And the non-recursive and the list directory one, it just lists out the entire directory. It's a simpler method, but it's less efficient and requires an extra join to get the full path. You can take a look at the difference in performance. Yeah, the memory usage is a lot higher, and I use it to get all the file paths of the Mac 7 data sets. So this is the actual joining of the data sets, if you may. It's designed to efficiently load and filter large CSV stock files. So it works by reading each file in chunks, which helps manage memory when dealing with large data sets. For each chunk, it passes the date column and rounds the numerical values in the high, low, open, and close, because you need to know we are actually trying to highlight the upwards and downwards runs. So having it in such a very with a very high amount of like decimal points is not very conducive to that. And then afterwards, it combines into one clean data frame using pd.concat. Yeah. Okay. Overall, this function it does three things. It reads the CSVs, but it doesn't read everything. Otherwise, it would not be efficient. It reads it in chunks, and it also doesn't. It also removes some columns like adjusted column close, and it also converts the columns into a float. Okay, and that's it for the reading of the CSVs. So over here in this section, it says that we are only testing it out with the Apple data frame. This is so that we don't have to run through every single company in order to test the space-time complexity. And so, yeah, this section is mainly just measuring the space-time complexity of the different functions that we are going to be using. So right here, we have a baseline for the simple moving average for pandas. It basically just uses the rolling function. I could just use this, but in this module, it tests us on programming skill sets, which is why I'm just going to use this as a baseline, basically something that I hope to achieve, but realistically speaking, I'm not going to achieve this with pure Python code without even using NumPy. So first of all, we instantiate the rolling bin array with the closing values of the data set of the data frame, because we want to predict the get the trend of the closing column, the closing values with a window size of 30. So here we have a naive implementation that I showed you just now with the with the rolling bin array class. You can take a look at the difference in performance. Well, the difference doesn't actually seem that apparent with such a small data frame. But when you scale it up to a bigger data frame, this difference actually just adds up exponentially. So over here, we are just testing it out. Okay, this is just looking at what it looks like, and this is what it looks like with the simple moving averages of the last 10 values. Now we are moving on to the upward downwards array. Yeah, yeah. As you can tell, the performance difference, once again, not very apparent. What's the difference between 0.08 and 1.59? But it gets very obvious when you use really, really large data frames. So yes. Mhm. And this is the start of the actual feature engineering. Instead of just testing it on the Apple, we actually apply it all to using this function. And you can take a look at the performance. And also after that, we create this daily return, which is basically like the percentage difference from the previous day. That's what the daily return is. You can look at it from here. Yeah. And that is all for data wrangling from my part. Thank you very much for paying attention.
Hi, my name is Wei En and I'll be walking you through the code for our graphing portion of this project to generate what you see here on screen right now, which is the market trends of a specified company. In this case, it's Tesla, right? Where you can see the different lines denoting the high, low, open, close values of the data set, and also the moving averages calculated in the pre-processing stage of the data set. And you'll be able to see that it does general forecasting as well based on those moving averages, and also support and resistance lines on the graph as well. So at the start here, we'll be importing a bunch of libraries such as pandas for data manipulation, matplot and seaborn for our visualization, pickles for optimization that we will cover further on, and a bunch of pathing libraries for us to import our utility functions as described by Kevin earlier. Alright, at the start we'll be ignoring all those non-critical errors just for our output to look a bit cleaner, and we'll have the pandas to read the dataset and also pass the dates by changing the object type for string to change to date time objects for us to be able to plot into the graph. We're using .info for us to just check our importing was successful, and we can see that the date column, all the object types are date time. Alright, so that works. And over here, we'll be extracting all the company names from the ticker column while removing all those empty spaces and making sure that none of them are recurring. So we'll have the max 7 companies here: Apple, Amazon, Google, Meta, Microsoft, Nvidia, and Tesla here. And from the dataset, we'll be taking the column names and assigning them as their own respective variables for us to use during the programming. And the cell here is just a bunch of formatting of the graph and also adjusting the parameters for us to have it suit to our use case here. Okay, so I'll be explaining the naive way of plotting our graphs. Naive as in the sense that it's unoptimized, because this is our initial code for the graphing, and it's not very optimized because that every feature is all together in the point of that value and plot it as a straight line, right? So that will result in having the lowest recorded price as the marking for the line and the highest recorded price for the marking of the line. Yeah. And over here, this part of the code basically helps us visualize streaks in the trend of the data. So it will highlight green for increasing trends and red for decreasing trends. So over here with run group.shift, basically we're checking the changes from a day-to-day basis on whether or not it's an increase or decrease. So in this case, for positive trends, we'll mark it as +1. Negative trends, we mark it as -1. Alright, so and then it will take the cumulative sum based on the days of how many changes has been made. Alright, and record that now as a list. From here, we're only keeping a specified amount of days for it to trigger the highlighting. In this case, we've specified it to be 3 days. So what that means is it will only keep the data that has a minimum of 3 days of increase or decrease, right? So this is where it will plot the highlights. So it will highlight it green if the increasing trend has more than 3 days, and it will highlight red is a decreasing trend for 3 or more days. Right, and the rest of this code is just basically formatting the graph and inputting the parameters so that you have a clean graph right here. As you can see, the green and red highlights for recurring increase or decrease in trends. Yeah. And now I'll pass my time to Nigel to explain the optimized version of the code.
I am Nigel, and I will now be covering the second half of graph.ipynb. Starting with our modular way of plotting HLOC, moving averages, and predictions. This section shows our optimized and modular approach to plotting stock data. Instead of one long function, we broke the logic into smaller, reusable parts. For example, plot-based prices handles the core HLOC data, and plot moving averages overlays the trend lines for the 30, 90, and 180-day averages. This modular approach makes the code cleaner, easier to maintain, and faster to run. The plot predictions function handles short-term forecasting. It uses our rolling mean array class to predict the next 30 days of closing prices based on 3 window sizes, 30, 90, and 180 days, and plots them as dotted trend lines. This keeps the logic modular and ensures that only this function needs updating if the prediction logic changes. Next, we modularized the support and resistance logic and the highlighting of upward and downward runs. Each of these features were previously bundled into one function in the naive version, but now they each have their own role, improving readability and allowing better performance tracking. All the smaller functions come together inside the main plot stock data function. This version is much more efficient. Every component, like price plotting, moving averages, predictions, and trend highlighting, is handled independently and cleanly integrated here. We also used Python's Pickle protocol to save each generated chart. This means that the same graphs can be quickly loaded in Streamlit without rerunning the plotting code, saving both time and memory. To compare both methods, we used Tesla as our example. The naive version took about 0.94 seconds and used 2.4 MB of memory, while the optimized version completed in just 0.41 seconds and used close to 0 KB. So not only is the code cleaner, it's almost twice as fast and significantly lighter on memory. Lastly, we visualized the daily returns for each company. Here's the function that generates a histogram for the daily percentage changes. This chart shows the distribution of Tesla's daily returns. Essentially, how much the stock's price changed from one trading day to the next, expressed as a percentage. The x-axis shows the range of those daily percentage changes from negative to positive, while the y-axis shows how often each range occurred. You can see that most of the bars cluster around 0, meaning Tesla's price usually moves only slightly each day. However, the longer tails on both sides show that there are still days of larger gains and losses. Overall, this histogram gives a quick snapshot of Tesla's volatility. The wider and flatter it is, the more volatile the stock. The narrower and taller it is, the more stable the price tends to be.
Hello everyone, my name is Damien and here with me is my teammate Rainer. Today we are excited to present our stock analysis application, an interactive visualization tool using the Streamlit web application. This system consists of two main Python files that work in tandem with each other, display graphs and stock analyzer. First of all, I would like to introduce Streamlit. Streamlit is an open source Python framework specifically designed to create interactive web applications for data science and machine learning easily and efficiently. Streamlit was ideal for our project because it provides seamless integration with Matplotlib, allowing us to visualize data while turning complex charts and graphs into interactive web components with just a few lines of code. Moreover, Streamlit does not require HTML, CSS, or JavaScript knowledge, enabling us to build fully functional and interactive web apps entirely in Python. Its component-based architecture automatically handles user interactions, session state management, and real-time updates, making it ideal for creating data dashboards that can be deployed and shared quickly without compromising on functionality or user experience. The benefits of Streamlit made it ideal for our project, hence we decided to use it for dashboard creation where all the figures will be displayed. Let's start with displaygraphs.py. This is the brains behind our visualization system, and it handles all the chart displays, user interactions, and financial calculations. The class is designed with 5 key methods, namely the initialization method, display graphs on user select method, set view from month method, display daily returns, calculate, and lastly the calculate max profit method. And each of them serve a specific purpose in our visualization pipeline. The initialization function is designed to set up the visualization engine. As seen here, there are 4 variables that are introduced. So self figures is a private dictionary used to store all generated figures done previously. Tickers to use is a list containing all the ticker symbols of the Max 7 companies, while selected ticker uses the first ticker symbol in the list as the default ticker. From month is to set the default date to 12 months, and lastly, using the Pickle protocol, the corresponding figures will be loaded in and stored in the figures dictionary. Error handling is done in the case of undefined tickers, missing files in the figures folder, and if the Pickle protocol fails to load in the saved figures. Moving on to the display graph on user select method. This is designed to display the main stock trend chart with clear headers and helpful user guidance about the dotted prediction lines. The conditional checking done using if statements ensures that we handle cases where a ticker might not be found. Looking at the set view from month, this is one of our most innovative features. Instead of regenerating the entire chart when users want to see different time ranges, we dynamically adjust the x-axis limits. The calculation 20 by self dot from month by -1 converts calendar months to trading days, ensuring financial accuracy. This makes the figure interactive as users can select from which months they would like to view from. Error handling is done to handle invalid month inputs, missing ticker symbols, and insufficient data for graphs to be displayed. The display daily returns function displays the daily returns graph for the selected ticker. Using st.pyplot, the daily returns graph is retrieved from the figures dictionary and displayed on the Streamlit web application. Error handling is done in the case of a missing ticker, missing daily returns figure, or other errors outside of those reasons. And lastly, the calculate max profit function is to calculate the maximum profit that can be achieved from a list of stock prices under the assumption that stock could be bought or sold multiple times. The code ensures that the moving average window is either 30, 90, or 180 days. Then we extract prediction data itself from the visualization. This is done by finding the right prediction line from the matplotlike figure, which is the dotted prediction line for the selected time period. All the price points from that prediction data is retrieved, and using the max profit price function, all the predicted prices are used to calculate the maximum possible profit. This wraps up the display graph segment. I'll now pass my time to my teammate Rainer, who will explain how stockanalyzer.py works.
Thank you, Damien. So now let's examine the second file, stockanalyzer.py. So this is the face of our application and the Streamlit web interface that users will interact with. So the file starts by scanning our figures directory to automatically retrieve all available stock charts. It filters out the analytical charts to provide a clean selection list for users. Using Streamlit's component, we use st.title to set the title for the web application. st-select box is used to create a select box for users to select which stock they would like to see analysis for. So it will appear as a drop-down select box on the web application where all the company stocks are available for selection. Moving on, we create an instance of our display graph class and pass it on to the available stock figures. This seamless integration connects our visualization engine with our user interface. We will use Streamlit's column layout to display 3 key financial metrics side by side. So each metric calls the calculate max profit method with different time windows, giving users immediate insights into potential returns across multiple strategies. These values will be displayed on the Streamlit web application to show the max profit using simple moving average over 30, 90, and 180 days respectively. In this segment, we are creating a select box for users to choose how many months they like to view from. So there will be 3 choices, 1, 3, and 6 months are provided for users to choose from. The set view from month function from displaygraphs.py will be used to filter the stock data within the selected time window. The figure will then be displayed on the web application. And lastly, the graph for the stock's daily returns will also be displayed to the user. Here is a screenshot from our Streamlit web application where the stock analysis graph will be displayed based on the time window that the user wants to view from, which is 6 months. So these two files, stockanalyzer.py and displaygraphs.py, work together to help visualize the analysis done for each stock on the Streamlit web application. So displaygraphs.py manages all visualization logic and calculations, while stockanalyzer.py handles user input and interface rendering before displaying the results to the users in the form of a dashboard. So now I'll be passing my time on to Damien, who will be going through the live demonstration for our project.
So this is the Streamlit web application that we have managed to develop. As you can see, the title here is 1 year stock performance, and the drop-down box here is to select all any of the companies from the Max 7 the Max 7 ETF. And as we can see here, for the Amazon stock, we have done a max profit using SMA for 30, 90, and 180 days, and the values will be displayed here. And we have also done a line chart to show the trends of this stock for this particular year. And over here, we have the drop-down box to select from how far we want to view from. So this is showing the trends from 1 month ago. This is for 3 months. And this is for 6 months. And lastly, we have the daily returns for the particular stock. And this can be done with every other stock, like for example, Google. And when we select different stocks, the data will change accordingly. And now I'll pass my time back to Rainer to talk about our conclusion.
Okay, thank you, Damien. So to wrap up our video recording for this project, my team and I have developed a Python program that can analyze stock market trends for the Magnificent Seven companies to address the growing need for an accessible yet powerful stock market analysis tool for everyday traders. Through the integration and optimization of multiple modules we have programmed, this system can pre-process the datasets of the Max 7 companies and conduct financial analysis, presenting these calculations as clear and concise charts through interactive visualizations on Streamlit. So this brings us to the end of our video recording. Thank you.